Next, we will talk about the different boundary condition types that were listed in blue on the earlier slide. Velocity inlet boundaries are common boundary types for incompressible flows. A number of options are available for defining the velocity at the boundary. You can specify the magnitude of the velocity in the direction normal to the boundary. You can specify the components of the velocity vector, or you can specify the magnitude of the velocity and its direction, and you select which method you want to use here in the drop-down list on the panel. You have to specify turbulence values if you're solving a turbulent flow, and you have to provide thermal conditions in the thermal tab here if you're solving for heat transfer. Unless you're using a UDF or a profile, whatever values that you enter in the panel will be applied uniformly across the entire boundary. You can specify negative values for the velocity magnitude, and this causes the flow to exit the domain, so it's like you're prescribing the exit velocity. Velocity inlets are intended for use in incompressible flows, and their use is not recommended for compressible flows. Pressure inlet is another common inlet boundary condition type for CFD simulations. The required inputs include the gauge total pressure, and you can see the total pressure for an incompressible flow is defined as the sum of the static pressure and 1/2 rho v squared, and for a compressible flow is determined by the static pressure, the Mach number, and the ratio of specific heats. The supersonic initial gauge pressure input that you see in the panel to the right is only used when the flow at the inlet is locally supersonic. At a pressure inlet, you need to specify the flow direction. If you're solving a turbulent flow, then you need to prescribe turbulence quantities. And if you're solving heat transfer or a compressible flow, you also need to provide the total temperature. For an incompressible flow, the total temperature and static temperature are the same, and for a compressible flow, the total temperature is given by the expression that we see here in the lower right-hand corner. The idea of a pressure inlet boundary is that it represents a loss-free transition from the stagnation properties of total temperature and total pressure to the actual conditions at the inlet. In Fluent, the static pressure and velocity are calculated at the inlet, and the mass flux through the boundary varies depending on the interior solution and the specified flow direction. Pressure inlets can be used for both compressible and for incompressible flows. The other important inlet boundary condition type in Fluent is a mass flow inlet. The information that's required is that you have to provide either the mass flow rate or the mass flux. The supersonic initial gauge pressure input works the same as it did for pressure inlets, so this value is used as the static pressure where the flow is locally supersonic, or it's ignored if it's subsonic, and the value is also used if you initialize the flow field from this boundary. The total temperature works the same as it does for pressure inlets, and you have to specify the direction of the flow at the mass flow inlet. You want to be careful here because most of the time people expect that they're going to specify the direction normal to the boundary, but the default setting is the positive x direction, so you have to change the direction method here if you want it to be normal to the boundary. When a mass flow inlet is used, the solver has to adjust the total pressure to accommodate the mass flow inputs. So for compressible flows, this can be more difficult to converge than a problem with a pressure inlet. On the other hand, for incompressible flows, the opposite is true. Mass flow inlets are intended for use with compressible flows. However, they can also be used for incompressible flows, and they're a fully valid inlet condition for such a flow.